I think this is a moment to start. So welcome everyone to the MITP Seminar again. So today we're very happy to have Samir Murthy. So Samir got his PhD from at Princeton University under the supervision of Nathan Cyber, after which he did various postdocs and is now a professor at King's College London, and since September, I suppose, a visiting professor at the Institute for Advanced Study in Princeton. So Samir, we really appreciate that you're giving the seminar, and please take it away.
Thank you very much. It's a pleasure to give this talk. Thanks for the invitation. And as Vishnu was saying, hopefully this will happen in person sometime in the future. Should I admit whoever says they want to come in, or is someone else taking care of that?
Say that again, sorry.
So, in Zoom, people walk in and they say, please admit me. So is someone taking care of that, or should I keep an eye on it?
I only saw it now. Yeah, I'm taking care of it. Yeah.
Okay, good. Someone just came in, that's why I asked. All right. Yeah. So since I'm not there in person, please do ask lots of questions. That will be very helpful. My title is the Gravitational Index of the Heterotic String, and I'm told it's more or less an audience of string theorists, so that's where this is pitched. But again, if something is not clear, especially in the first part, please do interrupt. Even if it's a little bit unclear, I'm very happy to develop more or give references or anything of the sort. Okay, I'll just jump into it. I think that's the easiest. Oops. There we go. So consider any heterotic string theory compactification, which is supersymmetric and has at least one circle. Okay, so simplest example is just take heterotic strings on T6, a product of 6 circles. That's a 4-dimensional theory with 16 supercharges. That should be familiar for anybody who's taken a couple of basic courses on string theory. And in such a theory, consider a fundamental heterotic string which winds this circle W times and carries some n units of moment. Okay, it's some macroscopic object. And now if you recall your heterotic string theory, the supersymmetries arise from the right moving excitation. So it's in the free theory, the left and right movers are decoupled, and all the supercharges come from the right movers. So if you set the right moving oscillators to the ground states, then you get a supersymmetric state of the string. And that the mass of this BPS or supersymmetric state is completely determined by the right moving momentum Kr. Okay, with the usual formula. But the left movers can be excited as much as you want, and this string is still supersymmetric. And therefore, you get this infinite tower of BPS states. Okay, this was first studied by Dabholkar and Harvey. And it's a fairly easy estimate. It takes 5 minutes to estimate the degeneracy of states, how fast the number of such states in this tower grows as you increase the charges. Okay, and the answer is this. It's an exponential of 4 pi times square root of n double. Okay? Again, if you've done basic courses in string theory, something like this should be familiar, just the number of excitations of a free string. Okay. And the main question that is our motivation for this talk is what happens to this ensemble of states at strong coupling. So what this means is this description that I just gave you here was a free string. And now suppose you turn on string interactions a little bit, this description is more or less correct. But now what happens if you turn on the string coupling to be large so that the gravitational coupling constant in space-time becomes non-trivial. So this question, the similar type of question asked for different type of microscopic string configurations led to a lot of progress in understanding black hole entropy. Okay, so this I hope many of you are familiar with. So this was in 95. 1 year later, Strominger and Waffa asked a very similar question for not for the fundamental heterotic string, but for the three-charge system. There was a D1, D5, and some momentum. And they asked the same question: what happens to this at strong coupling? And the answer is it forms a black hole. And that led to the breakthrough that you can explain the black hole entropy as the entropy of this ensemble of strings.
Sorry, Samir, can I
Yes.
ask one question? So, are there any conditions in the formula you showed in terms of M and W? Are there any conditions on the relative sizes of M and W?
Yeah. Oh, I should have said this because I know people here have worked on this. Yeah, here I'm assuming N and W are positive. It's, let's say for the heterotic string, I think it really doesn't matter. It's supersymmetric for both signs.
Thinking a little bit along the lines of Cardy's formula, where M should be much larger than C here, M should be much larger than...
Oh, sorry, I misheard you. I thought you said sign and not size. No, so in this case, this relative size. So, okay, let me just run through how you derive this formula. So if you write the mass shell condition, you'll find that there's a left moving momentum and a right moving momentum. There's a kr square and a kl square. And what you really want to estimate is how many oscillators have been excited, because that's the thing that carries the entropy. And the mass shell condition tells you that the number of left-moving oscillators minus the right-moving oscillators, which is 0, is equal to KL square minus KR square. So if you, let's say you set KL square to be 0, just to be simple, then you just get KR square is precisely something like this. Okay, so the relative size doesn't matter. The relative size doesn't matter.
Okay.
And I think the relative sign also doesn't. Yeah.
Oh, okay.
All right. So now the question is, what happens to this ensemble? So as I said, for other configurations, this sort of has been successfully answered and has led to many sort of interesting developments. However, this original question, which was asked by Ashok Sen in 95, 1 year before, has still not been answered completely satisfactorily. And that's sort of my main motivation for this talk. Okay, I'll try to explain this, why it's, what is the issue. Before that, I want to clarify something. So in all of today's talk, so the general subject that I'll be discussing is really saddle points. So if you have this large ensemble of states, then in the Euclidean path integral, you expect a saddle point. And the question is to try to describe this saddle point. Okay? Now, in the gravitational regime, saddle point means that if G Newton is small, saddle point just means that you have a solution of the classical equations of motion. So GR, general relativity coupled to all the matter fields. So that's the kind of question I want to focus on. What are the gravitational solutions that are saddle points to various quantities that I'll be considering? Okay. And I want to distinguish this from the question of how to describe each individual microstate. Okay, again, people here in this audience have worked on such questions, and that's not something that I will try to discuss today. Okay. All right. So, I mean, that's an interesting question, and we can discuss this towards the end if there's interest. Good. So now, why is this? What is the issue about this this question that I raised? So you have this ensemble of double Karabi states. They're supersymmetric. So and they have an exponential growth. So the natural guess is that when you have strong, when you're in the gravitational regime, they will become a supersymmetric black hole. And all supersymmetric black holes have been non-extremal, so this will be some extremal supersymmetric black hole. And it's fair, this arrow was followed very soon after this question was asked. And it's fairly easy to write down a solution in the two derivative supergravity for this ensemble. You have two charges, so you make an ansatz of supergravity with two harmonic functions and you solve it, and very immediately you find a solution and you see that it's singular. The singular in that the horizon sits on top of the singularity, the black hole singularity. Okay. So that's not good. Then came the idea of what was called the stretched horizon. This has been extremely influential. The idea is that this singularity is really due to the fact that you're approximating the gravitational theory with the two derivative theory, so GR. But in general, there'll be higher order corrections suppressed by alpha prime. And once you put that, the horizon will sort of stretch out and will cloak the singularity and will form a horizon at string scale. Okay, there was this idea. And then people try to sort of realize this idea. It's a hard question technically because you're asking for four derivative theories of gravity to solve this equation of motion. But progress was made by assuming that close to the horizon of the black hole, there's a symmetry enhancement, as usual is the case for extremal and supersymmetric black holes. Okay, so you're in a T6 compactification, so there's always a T6 factor. And in the 4 dimensions near the horizon, you assume that there's an ADS 2 times S2 factor. Okay. Now, when the black hole is not singular, this can be proved. But now you have to assume it. But once you do that, then all the tensor structures are fixed, and then you can make progress, and indeed a lot of progress was made. However, there's a problem with this, which is that there's actually no supergravity solution known, which is exactly this. So the assumption here is that it's ADS 2 times S2 times T6, and near the horizon, and that's the symmetry enhancement. And because there's an ADS factor, there's also a supersymmetry enhancement. So Kevin is here. And the string breaks the 16 supercharges to 8 supercharges. And near the horizon, the assumption is that there's an enhancement back to 16 supercharges. Okay. And the statement is that there is no known supergravity solution with exactly this geometry. ADS 2 times S2 times T6 with 16 supercharges. Okay. So the best we have is 8 supercharges. Now, you might say, well, this is because we've not been tenacious enough to find this solution. But you can also phrase the same complaint in a slightly more formal way, which is that because all this is string scale, you should really discuss the symmetries. So here you have an SL2 times an SU2 times a U1 to the 6 with 16 fermionic generators. And there is no supergroup with exactly these generators, with these symmetries. Okay. So this is what I call a sort of kinematic problem with this proposal, because it has to do with symmetries. There's also a dynamical problem. And the dynamical problem is that there is another solution, which people call the self-gravitating string gas. This was originally due to Horowitz and Polchinski, which carry the same charges. So what this is that in the Euclidean string theory, the time circle is compact, and the heterotic string has the lowest mode of the heterotic string. When it winds around the time circle, at a certain temperature, it becomes nearly massless. So when it becomes massless, then it can condense. So there's a new degree of freedom in addition to the supergravity fields. And then these people found a solution where this thing has a wave. Okay, so that's the winding mode condensate. And recently, it was shown that, in fact, they found, Chen, Malderson, and Witten, that there's like a large manifold of solutions of this type, Horowitz-Polchinski type, which carry exactly the charges of the heterotic string, okay, with various different types of heterotic string charges. And then it was argued that the near extremal states are likely to transition here rather than to the black hole. Okay. Now, this last statement is interesting, and I don't assume it's completely familiar, so I just want to review this. If you know this, it's better with me. It's quite interesting. It's as follows. So there are two graphs. So the left one is the mass of the black hole divided. So fix the charge as we fixed it. So that tells you what should be the extremal mass and the extremal entropy. Okay, that's just given by the counting by supersymmetry. And then the y-axis is the mass in units of this extremal black hole mass. And the x-axis is the temperature in a certain scale that I'll come to, in units of a certain scale. Now, when the black hole is not supersymmetric, it has lots of mass, much bigger than m extremal. And then the black hole solution is perfectly regular. People have studied this. The horizon is large. And you can study black hole thermodynamics completely cleanly, very under control. And what you find, so what you can ask is, how does the mass behave as a function of temperature as you go towards the extremal mass? You can ask the other way around. How does the temperature behave as a function of mass? Now, you would expect that for an extremal black hole, as you come down, the temperature goes towards zero because it should be zero temperature. So you would naively would expect something like this. You see my arrow, right?
Yes, yes, yes.
Yeah. Okay, naively you expect something like this, but instead you find something like this, that the temperature actually grows at some place close to the extremal mass. This approximation breaks down for the reasons that we just discussed. The black hole becomes very small. So that's an extrapolation. This dotted line is an extrapolation, but it seems like you hit some temperature, which I'll call maximum temperature. Okay. Now let's look at this. You do the same thing for the entropy. You start following it. It's completely reliable. And at some point, you have to do an extrapolation. But if you do that, you find that the entropy is zero at this extremal temperature, okay, instead of being the extremal entropy. Now, this orange solution is the Horowitz-Polchinski type solution, which only lives close to this point, the extremality point. Again, there's regimes of validity and there's an extrapolation. Here, there's a bit of orange solid line. And if you believe the extrapolation, then indeed it's going the opposite direction and it goes in the right direction. So the final picture is that when you follow these black hole states towards extremality, it goes like this, and then there's a flip and goes to the Horowitz-Polchinski type solution, and indeed it goes to zero temperature, and it also has the right entropy. It has the entropy equal to the extremal. Okay, so this is the reason why these authors said that if you do this dynamical process, then the endpoint is more likely to be a Horowitz-Polchinski type solution. Okay. Now, so there are both these reasons, and what I want to do today is not this dynamical question, but ask directly what happens to the supersymmetric states. Okay, I just want to ask, if I just focus on the supersymmetric states, that it's clear what these states are in the microscopic theory, in the string theory. And you can ask, what's the gravitational saddle corresponding to these states? Okay, any questions so far?
Yeah, can I maybe ask one question about the previous slide? So the behavior of the mass and temperature here of the black hole, that is the typical behavior of an asymptotically flat black hole. It's this negative specific heat type of behavior, right?
Yeah, I missed one word. It's a typical behavior of what?
Oh, maybe, sorry. Do you hear me more clearly?
Yeah, it's slightly better, yeah. Mm-hmm.
Now I'm asking, so the behavior of the black hole, the mass versus temperature there, that's the negative specific heat behavior of an asymptotic.
Of a Schwarzschild black hole, exactly. It looks like a Schwarzschild black hole, whereas if you take charged black holes, like big Reisner-Nastrom black holes, they'll go this way. Right? They go to zero temperature, right? You cool a Reisner-Nastrom, you take a Reisner-Nastrom black hole and take M equal to Q, that has zero temperature. So indeed, this looks more like a Schwarzschild black hole, which is kind of surprising, given that it's supposed to be supersymmetric.
I see. Okay. So why is it behaving this way?
It's just the thermodynamics of you just have to solve the thermodynamics. Here it's completely reliable. In fact, Ashok Sen had done this in his old paper. It was not emphasized at that time, but you just look at you just heat up the black hole as usual. It's perfectly smooth. You ask what's the mass, and that's what you get.
What's T max?
Sorry, what is T max? T max is some number. As I said, it goes like this. You extrapolate and you get some number. It's something given. It's like some string scale number.
Okay.
I mean, maybe one technical. If you're asking technically why this behaves this way, it's important that there's a dilaton in the solution, as you know very well, in these solutions, and that sort of makes a difference compared to if you compare it with, let's say, Reisner-Nastrom, it makes a difference.
Great, thanks.
Okay. All right. Okay. So now you ask, what's the gravitational saddle corresponding to the supersymmetric? So I hope that is clear, right? So supersymmetric black holes you expect to be completely cool and zero temperature, and you ask, okay. So now I want to just focus on these states and ask, what's the gravitational saddle? Is there a gravitational saddle? Okay. So this is a well-defined question because there's an exponential number of states. You can just ask, what is the description in the gravitational theory of these states? Now, if I want to answer such a question, I need some observable which only focuses on those states, right? If I have an observable which, let's say, is only sensitive to the supersymmetric states, then I can ask, what is the nature of that observable as trunk? Okay. Now, such an observable has been with us for many, many years. It's the supersymmetric index, which was invented precisely for this reason, not for gravity, but to focus on the supersymmetric states. Okay. So again, just to put everybody on the same page, I'm going to run through the basics. I think all of you know everything I'm going to say here, but I just want to develop the language. Okay, so let's just take any quantum system with one complex supercharge Q, such that Q dagger is H, the Hamiltonian. Okay, so the spectrum is like this. There are non-zero, so H has to be non-negative. If H is positive, then there's a boson fermion pairing. And if H is zero, then you can have singlet states. Okay, that's the spectrum. It's very easy to see the representation theory. And now you calculate, this is the simplest index, it's the Witten index, trace minus 1 to the F, e to the minus beta H. Okay, beta is some temperature. And now I note that beta is the inverse temperature, and beta should be positive, not zero, in order to define this trace, because this tower goes on even in the regular quantum mechanics to infinity. And if you put a non-zero beta, positive beta, then that damps the high energy states, and it's a well-defined trace, okay, as usual as a thermal state. But as we all know, this trace is independent of beta because of this cancellation. Okay, whenever H is not zero, because of minus 1 to the F, there's no contribution. And so the only contribution comes from H equal to 0. Okay, and that's just the number of bosons minus the number of fermions at 0 energy. All right. The same argument also tells you that this index is invariant under deformations of the system, as long as the deformation is supersymmetric. The argument is exactly the same. If it's supersymmetric, it means this algebra is not deformed. The thing that changes would be the actual energy levels, but because of supersymmetry, the energy levels only go up and down in pairs, and therefore this index remains the same. So that's the basic index. And now I want to ask, what happens in the gravitational ratio? Okay, now the fact that this is invariant means that the index, if you calculate an index, it should have the same answer in the gravitational regime. But this particular index is kind of boring. It's just a number of zero energy states. That's not what we want for a black hole. Black hole has mass, so you want something slightly more sophisticated. Okay, so this is the basic index, but you can look at more sophisticated indices which calculate black holes. So here's one. This is n equal to 2 supergravity, and there are 8 supercharges. And now Q dagger is E minus the BPS mass. Okay, you fix charges of the black hole, BPS mass is fixed, and that's the super algebra. Okay, now the index is this. It's like the Witten index, trace minus 1 to the F, e to the minus beta E. Now, that's a little bit of a lie. This index actually vanishes because all the states except the vacuum state actually come in multiplets, boson fermion multiplets. But so the real index is called the helicity supertrace. You have to insert some fermion zero modes. Once you do that, it's a technical thing I won't go into, but it's fairly easy. You can do that, and at the end of the day, that just gives you a constant. And what you're left with is exactly a Witten index type of trace. Okay. So now you're in business. This index now counts states when E equals mbps. Okay, so this is the kind of index that we use for black holes. Similar indices have been used for black hole counting in many, many different situations. This was the type of index that was used by Strom-Benjamin. Now you do trace of minus 1 to the F. E, you write this algebra, it's Q bar minus mbps. 1 second. Sorry. Okay, so it's Q bar plus mbps. And now this part of the index, the first part of the index, is exactly like the Witten index that we just saw. Okay, so that I'll call d micro. Okay, and then there's e to the minus beta mbps. Okay, so this index that we have has this form. It's a number at fixed q times e to the minus bps mass as a function of q. All right. Now, for instance, if you calculate this for these the Volcker-Harvey states, you get exactly the same growth, e to the 4 pi square root of nw. And the question I want to ask is, what is the meaning of this gravitational? What's the gravitational meaning of this index? Okay, so as we just saw, if you can calculate this index at weak coupling, and you have a number. That number is guaranteed to be constant when you change coupling, assuming no wall crossings and so on, which I'm assuming. And the question is, what's the gravitational interpretation? What's the calculation in gravity, in the gravitational variables that gives you this number? Now, firstly, I want to say that this question is very general. So I've moved beyond, so I've sort of broadened my question to beyond this example that we started with. And for the next many slides, I'll stay in this broad context. Okay. And then at the end, we'll sort of evaluate, well, we'll localize back to this example that we started. Now, this trace definition of the index cannot be applied to gravity because we don't have a good Hilbert space description. But in the field theory, the trace can be converted to a path integral. And the path integral, you can write, at least formally, you can write a path integral in gravity, which is exactly equivalent to what we just wrote. Okay, so it's an integral over all the fields of gravity with the gravitational action. And you have a Euclidean time circle of size beta. And all the fields should be periodic around this circle, including the fermionic fields. That's what gives you -1 to the f. Okay. Of course, this is formal. We don't know the UV behavior of this path integral, but it's a good question as to what are the saddle points. That's a perfectly sensible question, which we should answer. Okay, so what are the saddle points of this path integral? This is the main technical question that I want to answer. Okay. Okay, any questions? I'll just pause for a minute.
Yeah, maybe a small question. So recently, people in sort of a different context, in 2D and also 3D gravity, people have been talking about the Euclidean path integral as being dual to some ensemble of either matrix models in the 2D gravity case, or most recently there was also by Jeffers et al. An ensemble defined of 2D CFTs that should somehow capture the Euclidean path integral. So how does that work here in the supersymmetric case?
Okay, good. Yeah. So okay, so we should postpone more discussion to after the talk, but let me just make some comments. So if you calculate, so one reason, sort of one broader motivation to study such things is exactly what you're saying, right? So if you have a particular theory, so in the old-fashioned way, let's say n equal to 4 Langmuir or whatever this Strominger for D1, D5 system, that's just one theory. There's no room for an ensemble, and you should be able to make all statements within the theory. And then you can ask, how does this compare to statements of that sort? So that's one reason one studies what I'm studying. And it turns out that there's a nice paper by Iliesu, Turiachi, and Kolulu, which shows that a lot of these some wormhole configurations and a lot of these configurations which are discussed in the context of ensemble averages do not contribute to the index. So there's actually a very clean way you can talk about a single theory. Okay, let's discuss more about that. That's a very interesting question.
Okay, thank you.
Yeah. Now, so what are the saddle points? Okay, it's an old-fashioned type of question. Now you might ask that why are you even discussing this? You know, for many years, I worked on it myself a lot, that the entropy of this degenerates, this index equals the entropy of a supersymmetric black hole. So isn't it that the saddle point is just a supersymmetric black hole, and that's the end of the story? And that's exactly what I want to sort of question. That was, I think, an implicit assumption in many people's minds. But in fact, there's some tension between this extremal black hole and the path integral. So let me explain that. So in gravity, when we talk about a black hole, we have something like this in mind. This is the Euclidean black hole. You have a Euclidean time circle of size beta. This is a radial direction. That's a two-sphere, let's say in 4 dimensions. And then when you go towards the horizon, this time circle starts to shrink, and at the horizon it becomes point. And that's the S2 that remains at the horizon. Okay. Now, extremal black holes, on the other hand, have beta equal to infinity. Okay. So that's sort of already different. And you have an infinite beta, and then the throat goes on for infinite sort of time, for an infinite distance, proper distance. Okay. That's very different from this kind of black hole that we're used to, which has a finite gap. Okay. You could ask, so I start with this because the microscopic index is defined with a finite beta. Okay, so that should be the dual. Now, you could ask, what happens if I try to fit the extremal black hole into this? In the sense that I solve the extremal black hole's equation of motion and put these boundary conditions. Then it turns out to be incompatible. You either get a singularity or you get a configuration which has zero entropy or something. Okay. So there's a clear tension. That's one tension. There's another problem, which is that, sounds technical, which is that the supersymmetric path integral that I had periodic fermions around the time circle, but this cigar type topology admits only one smooth structure, which is the opposite, the anti-periodic fermions. So it looks like it always breaks supersymmetry. Okay. I should say that independent of all this, there's been a lot of progress. So again, just to put this in some context, there's been an enormous amount of progress since Strominger-Waffe to explain and understand black hole entropy in different directions, and we've understood, a fair bit. But technically, all these methods relies on some kind of mix of Hilbert space and path integral. So you have the black hole as some point in space-time, and then you have to assume that there's a factorization of the Hilbert space of the inside the black hole and outside. And then outside, you can treat using usual quantum field theory methods. And the inside or near the horizon, you have to go to a path integral and do some ADS2 path integral. That kind of a method has worked very well and has been tested. You can show that this factorization really happens at the quantum level. There's a decoupling and so on. But it's a bit unsatisfactory because of this kind of mishmash of methods. And also because there are other gravitational situations like two-centered black holes, the same charges, and you want to put all of them into one uniform path integral framework at infinity. Okay, so that's sort of the philosophical motivation.
Samir, a quick question. It's Kevin here. There was an argument around this problem saying, well, you should consider near extremal black holes rather than extremal black holes.
Yeah, so you can.
That's what would contribute.
Wait, this argument by Sen and others, maybe you, I don't know.
Yeah.
Is that roughly what you're talking about?
Yeah. No, it's not me, but Sen. Yeah.
So that argument goes into this mishmash. So even after having sort of assumed a factorization, so the pure ADS2 path integral per se is not well defined. So you have to take a limit, but the limit is such that you sort of go to beta goes to infinity, so the tube becomes very infinite, and chase the horizon such that the horizon is at a finite distance. Okay? So as to always sort of consider an ADS2 black hole instead of ADS2. That's what you're talking about, right?
Yeah.
Yeah. So, but that limit, either of those two limits, you sort of completely get rid of infinity. That you have to. There's no way you can keep the infinite asymptotics at infinity and get an ADS2 or even near ADS2.
Okay,
so
thanks.
Right. Yeah. This is really, I want a non-extremal situation. And then I can take a limit of this as t goes to 0. All right. Now, the resolution has been known for the last 5 or 6 years. And the idea is to first solve the second problem, and that automatically solves the first problem, which is this, that you replace minus 1 to the f by a shift of the chemical potential for an R symmetry. Okay, so these supergravity theories typically have different R symmetries. You can have an angular momentum, or you can have some R symmetry gauge field. And you shift that by 2 pi I, and by definition, R symmetry means that fermions have different charges compared to bosons. So this precisely gives you a minus 1 to the f. Okay, that's the basic idea. So you give some holonomy to an R symmetry gauge field. And then you've converted the problem to a bosonic supergravity problem, which at least we know how to solve, try to solve. We try to solve it. Now, of course, such a solution will be complex. You've turned on some complex deformation. But it turns out that there are well-defined solutions, with a real slice which looks exactly like this, okay, which is non-extremal. Because you've turned on a chemical potential for R charge, the solution also carries R charge, even when the original black hole didn't. Okay, I'll give you an example which illustrates that point very soon. And then you have to go and calculate the action, and what you find is that the action, which is the free energy of this ensemble in gravity, is actually independent of beta. Okay, so it sort of solves all the things. It has all the properties that you want of an index. Okay. So it's supersymmetric. It fits into a size beta asymptotic circle. It's non-extremal, and the action, the free energy, is independent of beta. Okay, so this was first done here in this paper with Alejandro Cabubicet, Davide Cassani, and Dario Martelli. in the context of ADS5 black holes. And then that sort of developed into sort of explaining the CFT4 dual index and so on. And this was then extended to many different ADS situations and also to asymptotically flat space. This is what I want to focus on today. So in this paper that I mentioned, they did sort of pure supergravity in asymptotically flat space. And here this shift has a particularly nice form, very simple form. In pure supergravity, or in any of the supergravities in asymptotic flat space, there's no R-symmetry gauge field. It's called an ungauged supergravity. And so the only physical R-symmetry is the angular momentum. Okay, angular momentum by spin statistics is always an R-symmetry. So there's only one way to do this. You just take the angular velocity of the black hole and say beta omega is 2 pi I. Now, if you remember your Gibbons-Hawking, what Gibbons-Hawking said, they said that in gravity, trace of e to minus beta h times beta omega j is what this is calculating. But now if beta omega is 2 pi I, you get precisely -1. Okay, so this is the simplest situation, although it's came, it was not the first. It's actually a very beautiful way to a beautiful sort of playground to deal with these issues. Okay, in ADS5, there's all kinds of other technical things that are going on, and here it's very clean. Now, one thing I should say is that the black holes, this kind of non-extremal black hole solutions in asymptotically flat space rotate. Okay, that's what I meant here. While the Reisner-Nordstrom black hole in 4 dimensions, supersymmetric black hole, does not rotate. These solutions rotate. Okay, so I'll be discussing this. So today what I want to do is sort of lift this to string theory. Okay, so that was pure supergravity. Now we want to discuss some string theory compactification on Calabi-Yau. So this is n equal to 2 supergravity coupled to matter, vector, and hypermultiplets. And I want to present these non-extremal solutions, tell you a little bit about their properties. And now, in the old days, when people discussed, like 30 years ago, when people discussed black hole entropy in string theory and supergravity, one of the important points was what was called the attractor mechanism. The fact that so all the scalar fields and the entropy of the black hole get fixed at the horizon independent of the asymptotic model. Okay, there are also experts in the audience. And if you recall, the attractor mechanism had everything to do with extremality. In fact, you could even, like in Kevin's papers, you could even throw away supersymmetry, have only extremality, and you still have an attractor mechanism. So here I want to do the opposite. I don't like extremality for the reasons that I said, because you want to put it in a path integral. I keep supersymmetry, but then what happens to the attractor mechanism? So it turns out that there's a nice new story, which we call the new attractor mechanism. This is a paper with Jan Boruch, Luca Eliesiu, and Joaquin Turiachi from last year. So that's the second thing I'll tell you about. And the third, then finally, I'll specialize to this heterotic string system, where also there are some surprises. So this is a paper with Yiming Chen and Joaquin Turiachi. Okay, so that's finishes my introduction. I know it took a long time. Tell me how much time I have, please.
Like about 20, 25 minutes.
25. So yeah, it says 43 here, so I'm assuming 25 minutes. Let me just go on and you can stop me.
Can you maybe explain why supersymmetric solutions are not stable?
Can I explain what is not stable?
Why are supersymmetric solutions not extremal in this context? I mean, you would expect naively.
Okay, that's exactly where I'm going now. Okay, so let me tell you. So let's take the simplest construction. Okay. So let's just take pure supergravity. Pure supergravity means it's just Einstein-Maxwell theory. Okay, so let's just illustrate it here. So the question is, are there such solutions of the type that I'm discussing at all? Okay, so let's start from something that we know. So let's start with the extremal Reisner-Nordstrom black hole. Okay, so so let's say it's an electrically charged black hole of charge q. So you have one harmonic function that determines the full solution. Okay, this harmonic function is 4 dimensions. Harmonic function is a source sitting at x equal to 0, r equal to 0. And then the metric is written in terms of this function, and the electric field is also written in terms of this function. That's the full solution. It's very easy. And you can essentially, as x goes to 0 is the horizon, or I'll call it r, the absolute value of x. R goes to 0 is the horizon, and you can essentially eyeball how you get the ADS2 times S2 over here. So it's important that this blackening factor has a double pole at When r goes to 0, this just looks like 1 over r square. So there's an AdS2 from here, and then there's an S2 at finite radius. And again, if you just stare at it a little carefully, you'll see that the area of the black hole is 4 pi r square. That gives you this entropy, 4 pi q square, excuse me. Okay, this obeys M equal to Q. This is the supersymmetry solution and a supersymmetry condition, and it admits killing spins. Okay. Now, this solution does not rotate, okay, as you see here from the metric, but you could have said that a priori because there is what is called an extremality bound on Lorentzian solutions. Okay, this is a condition of regularity of the Lorentzian conditions. Typically, that there's no naked singularity, no closed time-like curves, this kind of regularity conditions. And in this case, what that says is that the m square should be greater than or equal to q square plus j square. Okay, this is not a condition of supersymmetry, just a physical solution, something about the solution in supergravity. Now, if m square is greater than or equal to q square plus j square, and you impose m equal to q, you just get j equal to 0. Yeah, that's a quick way of saying why these black holes don't rotate. Okay. And then because you can see that at m equal to q, this solution is extremal because of the double pole, you get that the Euclidean continuation is the 0 temperature infinite tube. Okay. So that's the usual story. Now, I want to discuss the new one. So now the solution I'm discussing has 2 harmonic functions instead of 1. Okay, I'll call it v and v tilde. And that's the solution. Okay, so v tilde replaces v square. Now you see that the solution has rotation. Okay, this omega e is a one form. You can think of it as a 3-dimensional gauge field. We call it the rotation gauge field, whose curl is determined by v and v tilde. If you think of v and v tilde as 2 sources, what I've done is I used to have one source at the center, sort of made it into 2 sources. One at what I call the north pole and one at the south. Okay, such that the total monopole charge is the same. But what I've done is to introduce dipole fields. Okay. So the electric fields, everything is determined here. The fields determined by v and v tilde. You see that as r goes to infinity, the electric monopole field remains the same, because when r goes to infinity, from very far you don't see the separation. But if you look at this equation here, you see that there is a magnetic dipole field that has developed in the solution. Okay, which of course when v equals v tilde, then this dipole field disappears. You go back to the extremal solution. Okay, this turns out to be sort of the most. Todd asked this question: what is the most general supersymmetric solution in this kind of theory? And this is the most general supersymmetric solution with these asymptotics. Now, this has m equal to q. It's supersymmetric. It admits a killing spinor. However, it's non-extremal. You can see that clearly because there is no double pole in this blackening factor. Okay, the 2 poles has been sort of desingularized into double pole has been desingularized into 2 single poles. Okay, and this single pole is here is integrable, so you get a finite distance to the horizon. You get a K. Okay, now if you worked at all in this kind of business, like Vishnu was asking, you should immediately say this is not allowed. What is going on? And the answer is that the Lorentzian, this black hole doesn't have a good Lorentzian continuation for the reason that I explained. The Lorentzian theory has a naked singularity, it has a naked ring-like singularity. Okay. However, what we are concerned about here is the saddle point to the Euclidean particle, and there's a perfectly good smooth Euclidean continuation. By that I mean a certain section of this complex solution. Okay, that's been explained in this paper by Hartley and Hawking. So you think of this omega as a 3-dimensional gauge field, and then because of this equation, you see that there's a Dirac string for this gauge field. And if you want the solution to be non-singular, then this Dirac string can't just hang. So it has to start and end somewhere, and that's what you call the north and south pole. Okay. Once you do that, you can figure out what is the behavior of the various fields around it, and that gives you a certain condition of smoothness. This is like the Dirac sort of no singularity condition. And what you find is that the distance between the 2 poles gets fixed in terms of the charge and the temperature, and the angular velocity also gets fixed in terms of temperature to be precisely what we want. It's beta omega is to pi. So it's very satisfying that the condition of local supersymmetry plus smoothness gives you exactly the condition, global condition that we put from infinity. Okay, so another way of saying is that this is precisely a saddle point of the index that you started with. Okay.
Should I be worried about?
Sorry, say again, please.
Are you worried about these things decaying because of non-extremality, or is supersymmetry protect this from decay in some dynamical problem?
Again, so the question is, am I worried about this thing decaying? Is that roughly the question?
Yeah. There's also supersymmetric, so which wins?
Yeah, so these are, I think of these as just saddle points of the Euclidean path integral. I'm not talking about kinetic.
Okay.
But they're supersymmetric, so in that sense, they're stable.
In what sense?
Yeah, go on, sorry. Sorry,
in
somebody
what
else.
sense is this horizon? Yeah, so it's Kevin again. In what sense is this horizon a horizon? If there's, is this horizon in the Lorentzian section, or
No.
The
Lorentzian section the Lorentzian section has some naked ring-like singularity. This is just
okay,
it's the horizon in this sense that we think of Euclidean horizons here. Yeah. Right. So in the Euclidean path integral, what do we mean by black hole type saddle points? You have some finite circle. You ask, is there a solution where that shrinks, and then there is the rest of the space remains finite. It's a horizon in that sense. If you have that, you can calculate its free energy, and you'll get some typically an exponentially growing entropy. Right? Sorry, exponentially growing path integral, partition function.
So it's where some S2 goes to. Okay, thanks.
It has, so when I draw these pictures, I've taken some real slides of the complex solution.
Thanks.
So yeah, okay, good. So I mean, what I'm saying is that another way to think about it is the horizon in the sense that it's the hole in space. So from the Euclidean theory, you can think of black hole as a hole in the Euclidean space-time. It's exactly that. Okay, and it's the size of that. Now, I presented it in a way which may or may not be familiar to all of you, that there is this parameter A. But now if you think about it, it's whether Euclidean or Lorentzian, this is a black hole type solution, as you'll immediately recognize from this metric. It has mass, it has charge, and it has rotation. Okay? And indeed, the only thing it can be is a Kerr-Newman solution, and that's what it is. We have to go through some change of coordinates to see that. And A is exactly so this, to focus on that. So M equals Q, and A is this J over M. Okay. In fact, that was the motivation. So before Todd, Israel and Wilson and Perges, they actually discussed the solution from this other point of view. They were looking at the Kerr-Newman metric, and they said, what is the limit when M equal to Q? They got this, and they discussed various properties. They also realized it's not a good Lorentzian solution. So sometimes these things are called IWP metrics after the authors. And now one interesting thing is that the on-shell action of the solution obeys the Gibbons-Hawking relation with respect to the parameters that we have. So we fix the charge, so that only leaves mass and angular momentum. So the dual to the mass is the entropy, and then dual to the angular momentum is this Legendre transform with respect to the angular velocity. And you find that indeed the on-shell action is minus beta times the BPS mass, that's Z infinity the BPS mass, times plus these two terms. Neither of these two terms is particularly nice analytically. They both depend on the temperature. So in particular, the entropy depends on the temperature, beta. But by temperature, of course, I just mean I'm calling beta temperature. It's something in this complex direction, the non-extremality parameter. But the sum of these two entropies is very nice. It's exactly the extremal entropy. Okay, so the value of the action is minus beta times Q plus the extremal entropy, exactly as you would expect from the index, the exponential minus beta mbps times the e to the entropy. Now, so that was that. Now, let me just tell you briefly about general n equal to supergravity. So the theory is a theory of the graviton multiplet coupled to vector multiplets. So each vector multiplet has a gauge field A, complex scalar, which I'll call Y, and some gaugini. And the black hole carries charges, electric and magnetic charges with respect to all the gauge fields. And the two derivative action is completely determined by the prepotential, which I'll call G of Y, which is a homogeneous degree 2 function. Usually people call it X and F of X, but this is some rescaled version, so I'm calling it Y and G of Y. And in the string theory, type 2 string theory, on a Calabi-Yau threefold, this G of Y, the leading order is completely determined by the triple intersection numbers. It's this cubic prepotential. And now the most general supersymmetric solution in this theory was also, so people ask this question, what's the most general supersymmetric solution? And the answer is again this IWP type of metric. So there's a blackening factor and a rotation. The rotation is, yeah, so the solution is determined by a bunch of harmonic functions. So if you have some number of gauge fields, to each gauge field, you have to give two harmonic functions, exactly like in our pure supergravity example. So I'll call it H and H tilde. And this rotation gauge field is completely determined by the harmonic functions. And the blackening factor is determined by the scalar fields. Gi is the first derivative of the prepotential. And the scalar fields are themselves determined by the harmonic functions. So the harmonic functions here I've shown you completely determine the solution. I've not shown you the electric fields, but they're also determined. Okay. So this has been studied again, well, from various points of view. And again, if you specialize these to, let's say, when all the sources are at one point, you get back the old extremal attractor. Okay, you get some gamma as the charge, 1 over x. And as x goes to 0, you find that all the fields go to constants at the horizon, spherically symmetric, and the value of these constants are determined by the charges. Okay, so these scalar field equations are algebraic. And in the spherically symmetric situation, they just determine the value of these constants. They're called the stabilization equations or the attractor equations. And you can, in principle, invert this to find the solution for the scalar fields in terms of the charges. And then you see that in this limit, omega, the rotation becomes 0. And then you can find what is the area of the horizon. The area can be written like this. You can write it as a Legendre transform of the value of the prepotential, imaginary part of the prepotential at the horizon. Okay, this was first written by Cardoso, DeWitt, Mohaupt, and Capelli. And then Oguri, Strominger, used this in a very nice way in the quantum theory. Now, the type of solutions we have now, again, we just split it into some north and south pole. So by doing so, you introduce parameters. So you have the total monopole charges, which are constant. But now you introduce dipole charge, both for electric and for magnetic fields. So I'll not present the whole solution. I'll just tell you what the data and what the solution are. So the data are these, the monopole charges and the temperature or the angular velocity. And the parameters are the dipole charges and the size, the distance between the two centers. And now you have as many BPS equations as the number of vector multiplets. So as many dipole charges plus one real smoothness condition. So you have as many equations as parameters. So in principle, this is you'll have solutions. Okay. So let me just contrast the old and the new attractor mechanism. So the old attractor mechanism was like this: that you have a spherically symmetric black hole, and all the scalar fields become constant at the horizon, determined by this attractor equation. And the new attractor solution looks like this: that it's not spherically symmetric; it's rotating. And the scalars are not constant on the horizon. They depend on the angle on the horizon. They depend on the temperature, and they depend on the asymptotic moduli. Okay, so everything goes out of the window. However, near the poles, so there's a clear north and south pole. Near the poles, the fields, the scalar fields, are determined by the charges completely. In fact, they're exactly the attractor value. But now there is this complex split. So near the north pole, the holomorphic part of the scalar fields get their attractor value, and the anti-holomorphic is 0. So you can see clearly it's a complex solution. The y bar is not the complex conjugate of this. And near the south pole is the opposite that happens. Okay. And then you can check that the on-shell action also, so if you can write this in this nice way, that it's a Legendre transform, but now there is one Legendre transform holomorphic at the north pole and one anti-holomorphic at the south. Okay, now these two are independent. Okay, I have 2 more slides for the heterotic system, but I could also just stop. I mean, it's up to you. I can just wrap it up.
No, you still have 5 minutes or so.
Okay, so then let me just charge on. So now I can apply this. So this I think is one of the sort of lessons, that there is this very nice attractor mechanism. Now you can apply this to this heterotic problem. So for the heterotic problem, the cubic prepotential. So to calculate the cubic prepotential for the heterotic string, it's easy to go to the type 2 dual frame where the Calabi-Yau is K3 times T2. In this case, everything is determined by the double intersection numbers of K3. And there are 2 charges, N and W, which is 1 electric and 1 magnetic charge. And you can write this new attractor solution like I just showed you. The problem is that this is singular. Okay. So when we started this project, we thought that because you've sort of desingularized the solution by rotation, this will automatically solve this heterotic string problem. But that doesn't happen. It's a nice, it's a nice solution, but the metric is completely smooth in this frame. But the heterotic dilaton, one ratio of the scalars, blows up at the poles. Okay, one of them is 0. Why? This is P1 and this is 0. Okay. What that means physically is that it blows up with a sign such that the G string actually goes to 0. So it's a funny kind of singularity. So in the Einstein frame, everything is smooth, but G string goes to 0. But what that means is that the string frame is singular. So then we're back to the old problem of having alpha prime corrections. Okay. And the same conclusions can be reached instead of this kind of supergravity, n equal to supergravity. You can directly do heterotic string theory on T6. That was done in this paper, and we also had some chapter on that. And so in order to, so the advantage of this formalism is that now you can include higher order correction. So this is the prepotential. I should have called this G. In addition to this prepotential, you can start adding higher order correction. So the first correction is like this. It's y1 over y0 times some field called epsilon, which is a 4-derivative Wild square tensor that is supersymmetric. With a coefficient, which is 1, I'll just call this C. Again, it's a much harder problem. And now it's really hard because we don't have an ADS2 symmetry. There's no extremality. But in fact, the full equations were analyzed in this heroic paper. And we sort of took that and we first showed that indeed the equations near the poles, so the full equations are not algebraic, unlike in the ADS2 situation. But near the poles, they again simplify and you get algebraic equations. And in fact, you get back the attractor values. Okay, and then now you can see the C here, C is 1, but I just put this here to show that it's important to put that to get a non-singular value. And so you get this kind of a solution. Now, of course, this is just one particular 4-derivative term, but it shows at least that this can be desingularized, properly desingularized. And the action of the configuration is difficult. Now you have to sort of integrate this 4-derivative action over the full cigar type geometry. We haven't done it yet. But if you assume that it's of the same type that it was, namely this Legendre transform of the prepotential, then it's easy to calculate it. And it just evaluates to exactly 4 pi square root of n. Okay. So that sounds like a bit of a miracle. And there's a partial explanation. The explanation is that this is a prepotential, what are called F-type terms, which are calculated by the topological string. And for a generic Calabi-Yau, this has an infinite expansion, but for K3 times T2, because of the 0 modes on T2, this actually terminates exactly here. There is nothing here after this. Okay, so the F-type terms are actually under control. Now I have to show that there's another type of class of supersymmetric terms one can write down, which are full superspace integrals. I have to show that those don't contribute. Those are harder, but in the ADS2 situation, we actually managed to show that. So hopefully we can do something like that. Okay, so I'll just end with some summary and outlook. So firstly, I defined something called a gravitational index. Okay, so that's like the usual Witten index or supersymmetric index, but written in terms of the gravitational variables. And I explained what are the saddle points to this index. And in all situations, we can calculate this equals the microscopic index as is expected by theory, but it's not at all clear what's happening in the middle when you transit from microscopic to gravitational variables. And one philosophical comment is that instead of thinking of this as a string black hole transition of two different things, in the supersymmetric picture, it's more like there are two dual pictures of the same thing, and it's just connected smoothly, and there's a constant index. There are all these other questions which we can now try to answer: other saddles, multi-centers, wall crossing, higher dimensions, and some of this is being investigated. Okay, there's some hope to localize the full path integral in asymptotic flat space. And okay, if you're interested in this, it's actually technically related to what people call bubbling solutions and fuzzball constructions. But the physics, as I showed you, is kind of different. This is more like a cell. All right, I end there. Thank you for your attention.
Okay. So thanks, Samir. Are there any questions? Maybe I'll ask the first one. Yeah, in the beginning of the talk, you mentioned this picture where you have where people are thinking that the microscopic index was somehow capturing this string winding comment.
Yes, yes, yes.
So are you now saying, I think maybe in your second point, are you saying that this supersymmetric Euclidean black hole can actually capture the right behavior? Is actually
yeah. So that's a very good comment or question. So yeah, so what I'm saying here is that these solutions that we're presenting, this Euclidean supersymmetric black hole, non-extremal, seems to be capturing the index in all the situations that we can, test. Asymptotic radius phi, asymptotic flat space, including this heterotic string. And yeah, so there's a smooth picture. Now, in particular for this heterotic string, it's a very good thing to ask, what about this third picture that I have? So there's a microscopic, there is one black hole, and then there's this third of Horowitz-Polchinski type solution. I'm not disallowing a third picture for the index, which would be something like a supersymmetric Horowitz-Polchinski type solution, which also has the right index. That's not unlikely. So, right? So yeah. It's for the same reason that if you start if you start going too close to extremality, then you have a regime where, both these pictures may not have good control. You've calculated it, the answer is good, but there might be a third picture appearing just close to the extremal point. So such solutions people have been trying to find such solutions without much success yet, but yeah, that's a very good question.
I see. So you're saying because the microscopic picture should apply, the index is always the same, right? It doesn't.
Yes. Exactly.
But the picture applies somewhere. Now you're saying the non-extremal black hole picture might apply sort of an intermediate regime, but sort of the full extreme, very close to the extremal point, you expect this Horowitz-Polchinski.
Yeah.
The correct description of the.
Yeah, exactly. Yeah. So there might be a Euclidean saddle of that type, which is also supersymmetric.
Okay. Any other questions? Okay. Well then Samir, thanks a lot again, and hopefully we'll see you at some point in South.
All right. Thanks, and thanks for having me. Yeah. All right.
Okay, Samir. Bye.
Bye. Thanks.